I'm going to talk about a machine learning project I've been working on at my company. And this could also be called How to Do Data Science with Limited Resources, actually. This could be an alternate job title, alternate talk title. Okay, first some things about me. So I'm a data scientist from Berlin. You know Berlin from our famous building, the Brandenburger Tor here. You also know us maybe for this weird-looking sausage here. And you also know us for building random walls, of course. But luckily, as everyone knows, David Hasselhoff single-handedly tear down our wall to give us all freedom. So we're very happy. So if Trump ever builds this wall, you're lucky to have him to tear it down again. Okay, my background is in cognitive science. I'm not sure how many people know this study program. It's a combination of a bunch of topics, and it's all focused on understanding how the human brain and the human mind works, and then also building it. So the idea is you can only truly understand something if you can program it as well, and then it works the same way. So you have a bunch of topics like neuroscience, psychology, philosophy, and also the tech side of AI, computer science, and statistics to build it. Turns out it's a really nice introduction to, or really good preparation for a data science job, so can highly recommend it. Now some things about my company. I don't expect many people in the audience to want to buy an e-commerce platform, so this is not a sales talk, but just that you understand the context of where the project that I'm working on originated from. So the company is called commercetools, and we are selling software to manage e-commerce platforms. So our customers are people who want to sell something online. So here you have a typical e-commerce store. You have a bunch of products and some information where you can filter for sizes or for colors and all these things. You have images, you have product names, you have product descriptions. So this is the domain that we're working in. And the main product that we're selling is a REST API to manage online shops. So this is actually a developer-friendly way where you can manage these things. Maybe a quick question. How many of you know what a REST API is? Okay, that's enough, I think. For the people who don't know, think of it as a way where you communicate, where you can request data from the web or request certain processes to trigger. So you just have to do a request here. I don't know if it's big enough for you to see. You can do an HTTP request here. You have this URL, and then you can enter as a last endpoint here products, and then you get some information about a certain product here, like the product name or the product ID. So this is the stuff that we're dealing with. And in our API, we have endpoints for products, but also APIs to manage categories or to manage carts. So what people, when they shop online, put in their cart, when they make orders. And so to manage all these processes and integrate them, this is what the company is about. And apart from this API, we also have a user interface where you can have a graphical interface where you can manage your online shop and all your data. So this is the domain that I'm working in. Now about the machine learning projects that are going on at my company. So we are mainly working on features that can make it easier for our customers to manage their e-commerce shops. So anything that might speed up some time or that might clean up some wrong data or improve the data quality, anything that relates to this is what we're doing. And here's a little overview of the projects that we're working on right now, so that they have a bit of an overview. So today I'm going to talk about category recommendations. More on that later. This is about you have a certain product, and then you should recommend in which categories it should fit. So is it a T-shirt? Is it a shoe? Does it belong to men or women? These things. Other things we're working on is to detect similar products. So in the data that we have, it can often happen that people add a product twice, and sometimes they have very large product catalogs of like 100,000 products or more. And so it's hard to find when somebody made a mistake and added a product twice. So we use some methods from machine learning to estimate how similar are products and how can we find duplicates. We also do a bit of fraud detection to find out if there's an order that has been made which is suspicious and which might be fraud. Data normalization is basically about cleaning up dirty data. So you can imagine you have a product Let's say a T-shirt, which has different sizes associated with it, which could be small, medium, large, extra large, and these things. And when people enter this data in our database, it can happen that they have some inconsistencies there. So sometimes it's lowercase, sometimes it's uppercase, sometimes there's a shorter version of it, and we are developing something to automatically map that to a fixed scale, so to clean this dirty data up. And we're also thinking about, so we haven't done much in that direction, but the next thing would be recommendations for missing data. So whenever there's a certain field, there's a product image missing or there's a product description missing, we want to recognize these missing fields and recommend values how to fill them. So anything to make this easier. And just a short overview about the tech that we're working with. So we're working with Python. Maybe also short show of hands, who has programmed in Python before? Okay, excellent. So I'm sure you know most of this stuff. This is just a typical Python data science stack. So for neural networks, we use TensorFlow or Keras. For our APIs that we develop, so how we publish our machine learning services, we use Flask. I couldn't resist putting PyCharm here, which is probably most of you know it, is a highly recommendable IDE that just makes it much easier to notice anything that, any dependencies that you have in your code or any syntax that's not PEP8 compatible, so can highly recommend it. And all of our platform runs on Google Cloud, so the rest of our database as well, and also the APIs that we develop in the machine learning team. Okay, now to the project that I'm talking about today, category recommendations. So this is a typical e-commerce store that you have here that you probably know. Up here you have some categories which offer a way to navigate through the shop. So you have shoes or shirts or all the products categories, and then you can navigate into subcategories to find the product that you are interested in. And now a common problem with this is that it's hard to assign categories to products because there's just a lot of change. Products get added to the database on a daily basis, and some shops have thousands of categories and nested attribute structures, which makes it hard to maintain this and hard to maintain to keep this clean. So our idea was to develop a machine learning service which can automatically recommend categories for a given product. This is the basic idea. So now we are, so this is one example of a category hierarchy. So you have the category fashion. This nests into men and women, and then sports and business, and then shoes and pants. And then you can have products like these. So this would fit to the category sports and shoes, and this would fit to the category women and shoes. So there's a complex nested relation between these things. And now when I say that we automatically want to recommend categories for products, I'm not saying that we just want our customers to click a button and then automatically categories get assigned. This, first of all, wouldn't work because the accuracies are not high enough for this when there are thousands of categories. But it would also not really be practical because customers always know more. Our customers, so the people who manage e-commerce platforms, they always know a bit more. They always know, okay, this particular product might fit into this category, but in this case, I don't want to put it there. So our idea is basically here to give a pre-sorting of categories. So we do not want to directly assign them. We just want to show them, okay, you have this product. These are the categories that we think are most relevant. So if you want to assign categories, look at these first. So we think of it as a pre-sorting of categories. Okay, now I'm going to talk about a bunch of challenges that we asked ourselves when we started this project. So the first challenge is that every online store has a different category structure. So remember, our customers are different online stores. So there might be one store that sells groceries, one that sells fashion, one that sells home supplies, one that sells skiing equipment. So they all can operate in very different industries. And even if they operate in the same industry, they usually have a very different category structure. So you can have a product like here, like a jeans. And in one store, this might fit to fashion men jeans. And in another store, this might fit to clothing pants. So there's a lot of variance there. And if we want to build a machine learning model that recommends these categories, it's not easy to figure out what you want your classes to look like. So we considered two options, how we could approach this problem. The first option is to build multiple store-specific models. So the idea is just we have a bunch of different customers, a bunch of different stores, and in order to recommend categories, we just train a separate machine learning model on every data set from our customers, and then this machine learning model is highly specific to the categories that the store actually has. But of course, you can imagine the more customers you have, the more models you have, and it's a bit harder to develop the infrastructure for this. The other option, which we actually went with at the end, was to build one general model. So as you have it here, you have just one machine learning model, and this recommends general categories. So when I say general categories, I'm talking about categories that cover the most use cases of our customers, more abstract. And once you have these general categories, you can match them to the specific stores. And so about this matching procedure, I'm going to talk about it later as well. But just a little preview, we used some word-to-vec similarity matching for this. But so just that you get the idea, so we just have one machine learning model that recommends categories, and afterwards there's just similarity matching to actually recommend only the categories that the specific store is interested in. Okay, some pros and cons. So if we would have gone with this approach, we would of course have better accuracies for stores with very specific categories. So let's say there's a store that sells very specific home supplies and has very detailed products with detailed sizes of nails and these things. If we use this approach and just try to infer these very specific categories from these general ones, this might be hard. So this, for the stores like these, this approach would be better. And also there's no category matching necessary, so you just can skip this step, which is better for the response times that you have in the end. But in the end, we went with this other approach because it just has way more advantages. First of all, you have more data per model, of course. So with option one, we can only use the data that the specific store has, but there might be some stores which have very little data, for which it's not really possible to train a reliable model. Also, the data is highly imbalanced. So if you have a store that might have thousands of T-shirts, but only 2 or 3 products for bandanas, for example, then it's hard to balance the classes out to train a machine learning model that's actually reliable. Another advantage of this is that it's easier to deploy, of course. So here you have an uncountable number of models, but a lot of models that you actually need to maintain, which is hard to put it in production. And another advantage of this is, of course, that you can also apply to stores with little data. So as I told you before, if a store has just very few products where you cannot really train reliable models, then this first approach doesn't really work for them, but this approach does. Okay, so this is just the general approach that we took. Yes? I'm coming to this. This is the next challenge. I can skip to this. So challenge, very large class set. So Amazon or eBay, they have listed 50,000 plus categories. So this is not your typical machine learning project where you want to classify an email as spam or not spam. So this is a lot more classes that you have to deal with. And as I said here, this part, general categories, it's a trade-off of how you select these general categories. Of course, you want to cover as many cases as possible. So this is an incentive to include more categories, but of course, the more categories you include, the lower your accuracies are going to be. So it's a trade-off, and we obviously haven't found the perfect solution, but we tested some things out, and for now, our current version has 723 model categories. So these are just some broad categories. You can see a selection of them here. So first of all, they are usually categories that fit to a larger range of products. And second of all, there are also categories that fit to the customers that we have. Because, we're not eBay and we're not Amazon. We don't need to classify 50,000 categories. We only need to classify something for our customers. And so we focus on the ones that actually cover the use cases of our customers. And so once we get more customers in other industries, then we can extend this to other categories. But for right now, this approach worked well for us with these 700 categories. And so this is the part about the class set. Last challenge. Product data is diverse and unbalanced, which complicates feature selection. So the question is, so we know we want to predict categories, but the question is, with what do you want to predict them? If you're working with products, you have a bunch of data like product names, images, prices, descriptions, sizes, brands, colors, expiration dates. And the issue with this is that there's a lot of variance, so there's a lot of missing data that you have to deal with, but there's also just a bunch of data that only applies to a subset of products. So for milk, for example, you might have an expiration date, and for groceries as well, but for fashion you have other attributes like the size or the color. So it's just heavily imbalanced, and so it's hard to choose a proper feature set. We decided to focus on product names, images, and descriptions first. So mainly because we think that these types of features carry the most information to predict categories. So if I show you a random, or not a random, but if I show you a product name and an image, you would probably be able to tell me which categories would fit to this product, whereas if I show you price and size, this would be harder. So names, images, and descriptions carry most information, and they're also available for the majority of products in our database, which is a big deal because we want to have features where we actually have some cases where you can predict from in many cases. So this is what we focused on. A bit confusing. I can hear someone else speak. Okay, just to recap a bit our approach after we went through these challenges. So the idea is to have an image model, a name model, and a description model, which recommends 723 general categories, which cover broad use cases. And then in the second step, we match these to the specific categories that specific customers of us have with a similarity model, which I'm going to talk about later. Okay, now let's dive into the machine learning part. So first about the model that we developed for product images. As will probably not surprise many of you, we chose a neural network for this. How many of you have worked with neural networks before? Raise your hands. I'm bad at counting. That's 70%, 60% maybe. Okay, I'll just give a brief introduction, but I won't make it too long. So neural networks, they are definitely the most successful model when it comes to image classification, and they have been used more and more in recent years, not because it's a major scientific breakthrough, but mainly because we have more available computing power to compute these networks. And it's loosely based on mechanisms in the brain. So I was a neuroscientist before, so that's why I needed to include a brain in my slides. This is just necessary. So it's based on the idea that we also find in the brain to build complex representations out of simple representations. So this is just a very efficient way to do information processing if you first compute some simpler stuff, and when you want to get information out of the more complex stuff, you just combine the more simple representations so that you can incrementally get more complex processes. So in the visual hierarchy of the brain here, whenever you see something in the early areas called V1, you first have some basic neurons which detect simple visual features like the orientation of a line. And then this gets more and more complex, where you can detect an edge of two lines, where you can detect complex shapes like squares or circles. And then you can combine these circles and these shapes to a whole face after you connect this in a complicated network. So this is how the brain computes representations for things like faces. And this is the little neural network introduction slide. Who wants me to skip this? Okay, not enough. So, neural networks basically look like this. So you have an input layer of units, and you have a hidden layer, and you have an output layer. In the input layer, this could be any variable that you want to use for your prediction. In the case of images, these could be values of pixels that you have. So this would be your input. And the idea of a neural network is just to approximate a function that maps from an input to an output. And in this case, you could map from an image to the model categories that we're interested in our project. So the input layer would have as many variables as the image has pixels, and then the output layer would correspond to how many classes we have, how many categories we want to predict. And in the middle of all this, we have a bunch of hidden layers whose job it is to extract features. So as I said before, this idea of building complex representations out of simpler ones. The first hidden layer looks at more simple representations, and the further you get in the neural network, the more complex it gets and the more complex the features are that are being extracted. And what we used for the image classifier is a convolutional neural network, and this has basically a similar idea of what I talked about in the brain and the visual cortex. So the idea is that in the first hidden layer that you have in your network, you don't take all the inputs that you have here, but instead you only look at a subset of the pixels to extract some local features, and then you combine these to more and more complex features to get some class predictions in the end. Okay, I'm not expecting you to understand everything about neural networks after this, but just as a short introduction. Okay, what did we actually do for this? So we used an approach called transfer learning, which we took, and where we took the neural network Inception v3 as a baseline model. So Inception v3 is a famous neural network which has been developed by Google, and it actually won the ImageNet competition in 2005. So this is how Inception looks like. It's just it's a deep and more complicated neural network, which is a convolutional neural network, and this has been trained on a large data set of, I think they had, in ImageNet, they have around 1,000 categories, and it has been trained on over 1 million data points. And I've heard in the training session at this conference that to train a model like this, it costs above 1,000 euros for sure. So it takes some resources and it takes time to compute models like these. But luckily, if you use an approach like transfer learning, you can just take this model that has already been pre-trained on a data set, and then you can fine-tune it to your specific problem that you have. And the idea of transfer learning is you just take this whole network as it has been pre-trained, and then you cut off the last classification layer. In this case, this has been trained on ImageNet data, but remember that we are interested in the specific categories that we want to predict for our application. So we just cut off this last layer and replace it with a layer that corresponds to the categories that we have. In our case, these 723 categories. And then you retrain this whole network, but you only retrain the weights from the last layer. And you don't have to retrain all these weights that occur in the neural network before that, which is, of course, much faster than training it from scratch. And it's just, you also gain everything that has been put into this, the modeling of this model. So you can compare it to, let's say you want to hire a certain person for your company, and the transfer learning approach would be if you hire an expert data scientist who already knows everything, and then you just have to tell him about the specific problems that you're dealing with at your company, which will, of course, be quicker for him to adapt to this because he already knows, he or she, I'm sorry, already knows how these algorithms work. And if you would instead train a neural network from scratch, this would be analogous to hiring a toddler, let's say, and letting him walk around the company. You need a lot of time, a lot of resources to be able to train him to be a proper data scientist in your company. And then after 30 years, he might be the perfect data scientist for your company, but you just have spent a lot of resources and able to get there. So it's cheaper to train someone who's already an expert and then let him focus on your specific use cases. So this was my cheap analogy for transfer learning. In order to do this, we used TensorFlow, and if you go to the GitHub repository of TensorFlow, there's a detailed description on how to do this transfer learning approach, specifically for this Inception v3 network. There's also a tutorial on this URL, which is just an easier introduction to how this works. I thought about showing some code here, but decided against it because it is, it's over 1,000 lines of code, and it's a lot of boilerplate code. I don't want to hate on TensorFlow right now, but for data scientists, if I would do it again, I would use the Keras API for it now. So Keras is a different machine learning library, which is higher level, so you have a lot less code, but you still have the same flexibility that you need for most use cases. You don't have the same flexibility, but you have the flexibility that you usually need if you're doing data science work. So if I would do this again, I would use the Keras API for it. But if you're interested in this TensorFlow repository, they have some detailed instructions on how to do transfer learning on this network. Okay, and for our case, we used a data set of 130,000 images, so which roughly corresponds to 100 to 200 images per category, which is not a lot of data, but this transfer learning approach lets us get away with it to some extent because we use a network that has already been trained on so much more data from ImageNet before. Okay, this was, yes? So the question was how I map this model to the categories that I want to predict. So as I said, this transfer learning approach, you replace the last classification layer in the neural network with the categories that you're interested in. In our case, these were the 723. And specifically, if you want to do this approach, what you basically do is on your file system, you have a folder with all your images, and then you have subfolders for all the categories that you want to predict. And in every category folder, you collect your images that you want to have that are examples for this category. And then this code basically just runs through your file system, gets all the image data, runs them through the whole network, and then runs the training on the last classification layer. Yes?
Are you going to go into the performance of your model?
Not really. We'll get to this later after I go to the similarity matching procedure. So on this pure network that we trained, our accuracies were at around 85-90%, but this is not really informative because this is just the model categories, right? And after these model categories, what we're really interested in is the predictions for the specific stores that we have. So there's a separate procedure that comes on top of it. And what we also found is that this models, for some projects, for some stores that we have, the accuracies are highly above 90%, but for some stores which have niche products like home supplies, very specific categories, the accuracies are way lower. So just one general accuracy score is not that informative, but it highly depends on the store that we're working with. Yeah.
And also, are you going to go into the infrastructure that you use for the different models? For example, did you deploy this particular model in CloudML on Google Cloud?
So where we trained it or where we deployed it? So we trained this network on Google Cloud. You don't have to. So with this transfer learning approach, if you train it on your machine and only train it on the data set, which is a smaller data set that we had here, it probably takes around 2 days to train on your machine, but we used Google Cloud ML engine for it. I'm not going to go into how you do this on Google Cloud. because this is the Open Data Science Conference. But it's very straightforward and very easy. I don't want to advertise Google right now, but you just write a YAML file, you say how many GPUs you want, and then you have your Python scripts where you have this code to do this image retraining, and then you submit it. But there are a bunch of tutorials for this. I'm not going into this. Actually, let me check the time. Okay. But yeah, apart from this, I'm not going to go into more details. I'm going to show you some Flask code later, how we wrote the API. But in the end, we deployed it on Google Cloud with Kubernetes, but I'm not going to talk about this. We can talk about it later. Okay. This was the stuff we had for images. Now let's talk about the model for product names. So these are some typical examples for product names. So men's heavyweight, blah, 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 size. So they are rather simple. So if you're working in natural language processing and if you're dealing with complex semantics of texts, this is not really relevant here because they are quite simple. I mean, if you want to predict a category based from a product name, if you do some simple keyword matching, this might not be the worst idea in the world. So if you just check which category names you have, and then you check whether the category name appears in the name, this might actually go a long way. But we still wanted some more flexibility there and some better performance. So we still train a machine learning model here. But of course, it's always important to ask yourself first, do you actually need machine learning? In this case, we think so. But a keyword matcher would have actually probably done not too bad either. So before you train a machine learning model on text data like this, there are a bunch of pre-processing steps that you need to consider. These are the ones that we experimented with. So you can consider doing automatic spell checking. So some product names have a low data quality. Maybe you want to correct wrong spellings first before you do anything else. Another thing that we have to do in our case, which is a pain, is translations. So the data that we have for product names is not always in English. In fact, maybe it's 50-60% in English. But we have a bunch of other stores which have different languages. So some product names are only in German, some are only in Swedish, some are only in Spanish. So the idea is to train the machine learning model only on English data. Of course, you can think about it. For some stores, it might make sense to train a different language, but just to make this whole process easier, we translate everything to English. And for this, we use Google Translate. Simple as that. So we just have, which actually, it works surprisingly well. Unfortunately, I haven't found an open source solution yet, which does as good of a job as automatic translation as Google Translate. So what we need is to automatically identify the language that we're dealing with, and then also directly translate it, and we use the Google Translate API for this if we have non-English words. So this is something that also goes into pre-processing. Then you need to tokenize your strings. So you have a name here, and now you want to know what are the individual units there, what are the individual words that you want to classify. You need to normalize it. So you need to, you don't need to, but in our case, we normalized all our stuff, so we lowercased it because we don't think that capitalization carries any important information which would be relevant to predict categories. And we also delete some special characters, so something like asterisk, which might occur in these product names. They probably don't carry any important information as to which category it is, so we just reduce the free parameters in our data to reduce these characters. You can also do lemmatization, which is basically finding a word stem of a word. So you can have, sometimes in a product name there might be the word apples, sometimes there might be apple, but for categorization this really is the same entity. So lemmatization just means finding the word stem of a word and getting rid of plurals and these things. We also experimented with phrasing. So if you have for example, the name Louis Vuitton in a product name. And then if you do this tokenization of splitting words, then your model might think that Louis and Vuitton are two different things, which could be used for classification, but it's really one thing, right? It's one entity, one thing that carries predictive value with what we want to do. So there are some approaches in the library Gensym here to automatically detect these words that often occur together, and then just make one entity out of them, for example, by adding a lower score there. And we also did some word removal, so this is also a common pre-processing step in natural language processing. So we removed stop words, so any words that we don't think are important for our predictions, functional words like and, or the, so any words which don't carry any content which we think is important for us. And we also have a blacklist of some words which we just found out during our analysis that they don't really add anything. So for example, the word sale, if there's a product name, t-shirt, blah, 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 on sale doesn't really have important information about to which category it belongs. And it's usually a temporary thing. So these are just words that we wanted to exclude and not have in our model. Okay, here's some code. The code examples that I have are just supposed to give you an idea of what we were doing. They are not, so they are simplified. This is an example of how you would pre-process these names. So for pre-processing, we use the Python library RE for regular expressions, and Spacy, which is for natural language processing. And if you want to write a function like this, which does some pre-processing, then here you can have the name, the raw string that you have here, and then you have an argument for the minimum word length. So in our case, we excluded everything that had less characters than 3, because we also don't think that these words carry much predictive value. So these are the words we excluded. And lemmatizing is optional. So this is the lower casing of the string that corresponds to this step here, the normalization. This is a regular expression which removes any strings that are not letters or numbers, and hyphens, commas, and dots, which we decided to include because hyphens, of course, sometimes carry important information for a thing like t-shirt. So if you have t-shirt, you don't want to let the model think that T and shirt are different things. So we treat hyphens as a special case. And we also kept dots and commas because they often indicate quantities which are important for e-commerce. But this is, of course, highly customizable. So this is not a perfect solution. There's a bunch of stuff you can play around with and see what works best, and this is what worked best for us now. But of course, there are many options there, and it's hard to find what the ideal steps for pre-processing are. And this is some stuff for Spacy. So if you use Spacy, you first have to load your language model. In this case, we loaded the model for English. And then with this line, you can parse your string that you have, and then it offers you a bunch of functionality like removing all stop words or removing spaces, which would be hard to do from scratch because you need to find out which are the stop words that you want to remove. For this, you need information about the language, and Spacy offers this. In this step, we remove any words that have less than 3 characters here. This is the step for lemmatization, and then at the end, you convert them back to strings, and you convert the list back to the string. So this maps from an original product name to a cleaned product name. Yes? Yes, I didn't include this because this is the final pipeline of pre-processing that we ended up with. For phrasing, I could recommend Gensym. I don't have code for this right here, but it's not complicated. There are a bunch of tutorials on the Gensym homepage how to do this. I mean, the basic idea is just it looks at your data set, it looks at the words, and it looks which words occur frequently together. So you can also code that yourself, but it's much easier to just take what is available in GenSim. But in the end, so we didn't use it in the end because it didn't seem to be necessary, and also because it just introduces some overhead, because you need, if you want to serve it in production, you also need this GenSim phrasing model, which you need to have available in your infrastructure. So this is just another step that you need to deploy, another step where things can go wrong. So we decided it doesn't add that much, so we excluded it. But yeah, I can recommend the GenSim homepage for this. Okay. Now we have a cleaned string for product names. Now we need to make numbers out of it, because machine learning models work with numbers and not with text. So there are a bunch of techniques for this, how to convert strings into numbers. A simple approach is so-called bag of words approach. So I'm sure at this conference you've had better introductions to natural language processing. This is just a Wild West introduction to some basic methods, just to give you an idea of what we did. So bag of words, the basic idea is you take your whole data set of all the text data that you have. Then you make a column for every word that occurs in your data set. And now if you want to vectorize one product name, you just take these columns and you enter a 0 when the word doesn't occur in the product name, and you make enter a 1 if the word does occur in the product name. So this is not a product name, but this would be an example sentence. The dog is on the table. Now you have just columns which correspond to the unique words in your data set, and whenever the word occurs, you enter 1 here, and then this would be the vector that represents the text that you had. Of course, you lose a lot. I mean, there's a bunch of disadvantages with this approach, because first of all, you don't have any information about the syntax. So here you just know which words occur in the string, but you don't know in which composition. So you lose information about the semantic relationships between words. And also this is highly sparse, because you have one dimension for every word that occurs in your data set. And you can imagine the larger the data set, the larger this vector gets, and it's just very hard to deal with and very hard to train robust models for this.
So how big was the beginning?
Good question. Not really sure. I mean, our word vectors in the end had 300 dimensions, but they used a different approach, which I'm going to talk about now. But if you take the full vocabulary, it will probably be, 12,000 words maybe. I don't know, a lot. But I can check if you're interested. Okay, a separate approach to bag of words is called TF-IDF, which stands for term frequency, inverse document frequency. Again, here I'm just going to try to give you an intuition. So this is a similar approach to bag of words, so it vectorizes words in a similar way like this. But the main difference is that it weighs words higher when they do not occur frequently in the data set. So the idea is if you have a word like the or a word like and, which occurs in a lot of product names and spreads across your whole data set, then this word probably doesn't carry a lot of important information that you need to predict something. So you would assign a lesser value, lesser weight to these words, like, for example, iPhone. So if I know that the product name contains the word iPhone, this obviously carries a lot of predictive value to recommend categories. So we want to weight this higher. Okay, and this is... I apologize for not taking the time to make this a proper formula, but this is how you basically compute the term frequency. So you just look at the number of times a word appears in a product name, and you divide it by the total number of words in the name. So this is the frequency of the specific term, which corresponds to one column here. And then you have inverse document frequency, which is the log of the total number of product names that you have in your data set, divided by the number of names with the word that you're interested in. And if you multiply these two terms, then you get a value, and then you enter this value here, which is just a more fine-grained measure that is more specific to, in terms of the predictive value of the words that they have. Okay, as you can see, this has a black border. This means we used it, if you haven't noticed by now in my slides. So this is what we used. I'll talk in a second about why. First, I'll talk about the last thing, the last approach that I want to talk about. So it's called word-to-vec. Compared to bag of words and TF-IDF, this approach manages to be a lot more dense in its representation, so it doesn't have these sparse vectors with a lot of zeros in them. And it also maintains a lot of the semantic information, so a lot about the information about how similar two words are. And if two words are very similar, they will have very similar vectors with this approach. So the idea is basically that you train a two-layer neural network that predicts context words from a word. So you have a certain word vector, let's say dog here, and then you enter this word vector in your neural network, and what you want to predict is the context of this word. So you can imagine that the word dog might, okay, let's take a different example. Let's take the word Nike, for example. If you have the word Nike in a product name, then in the context of the word Nike, you will probably see the word shoes more often than the word apple, just because this is how the word Nike is used. And in this word-to-vec approach, you just scan a string, and you look at the words and their context, and then you build a neural network that predicts the context of a word given the word. And after this, what you end up with is a dense representation which has these nice features. So these are some famous examples of word vectors. I'm sure most of you have seen this example. So you have a word vector for the word queen here. If you subtract the vector woman from this, you would end up here. And then if you add the vector for man, you would get king. So this is just an illustration of how these word vectors capture the similarity between different words, which is, of course, a very nice feature for your data, and which makes model training a lot easier. Okay, but still, in the end, TF-IDF worked better for us. The reason for this is probably because product names they just don't have a lot of complex syntax. So as you can see here, they barely have any syntax in them. They are usually just a concatenation of different words, t-shirt, size M, color blue, and this would just be an overkill for this. So TF-IDF is really a fast approach that worked well for our case, so this is what we used for this. This is just a short illustration of how you can do this in scikit-learn. There's a function or a class TF-IDF vectorizer in scikit-learn, and you can just call the function fit-transform and apply the names that you have, which is a list of strings, so a list of all the preprocessed strings that you have. Then you convert this to an array, and voila, you have your image vectors, your name vectors. Okay. After all of this, yeah? So if you get a new example and the words don't occur in the data set, yeah. So what I did there, I just added a zero vector for them, I think. I think if you just try to vectorize a word, so the question was what you do with words that don't occur in your lexicon. So if you run this machine learning model in production, and let's say there's a product name that only contains words that have never been seen in the data set, so the TF-IDF model wouldn't know what to do with this. And I think in scikit-learn you would get an error in this case, but we are catching these errors, and then we just add an empty string for these cases, so an empty vector. So you need to account for these cases where this doesn't, where it's undefined. But after we've done the pre-processing and after we've done the vectorization, we still haven't done any classification yet. So this is the classification which we've done. After all this pre-processing, we had a data set of 230,000 product names, which corresponds to roughly 300 per category. And we tried a bunch of models in scikit-learn, logistic regression, naive Bayes, random forests. XGBoost and support vector machines, so your usual suspects in these cases. And in the end, it turns out logistic regression performed best. Surprising, but I mean, it's the most simple approach from these ones. But given that product names are not that complex, that's probably the reason why this performed best, but I'm not sure. But so this gave us the highest accuracies. So we had, on the raw data set here, we had accuracies of around 92%, top 5 accuracies, that is.
So what are your labels? Because the classes don't actually exist. You created a special class set.
Mm-hmm.
So how did you get the 10 labels?
So we have our data set from our database with product names and product images and their corresponding category, right?
But those categories you might have only for the customers that you have, right? You just have those categories.
Right. So this comes down to manual work. So, I mean, for our customers, as you said, for example, we would have a category for T-shirts, but for one customer, this might be spelled T-shirts and sweatshirts. For another customer, this might be spelled differently, capital letters, but this comes down to manual work. So I just looked at all the data set that we have, and then I said, okay, these categories are T-shirts, so I standardized all these categories to the category set, these 723 that we selected. Of course, it would be nicer to have this automatically done, but I don't think it's reliable enough. So there's too much variance and you mess up anyway. So I did this manually just to automatically assign this. Okay. I'm sure most of you have seen examples like these. So this is just how you train a basic machine learning model in scikit-learn. You can import this logistic regression class here. You can import a function to train your test set and your training set. And with this line, you train your data. You split your data into training and test data. With this line, you fit the model to your training data. And with a function like this, you can predict something for new examples. Okay, this is the most sophisticated slide I've ever done. So after we've done all this for product names, we wanted to find out what would be the best model for product descriptions. And long story short, we used the same pipeline for this because the same approach seemed to work out best. So the same combination of TF-IDF and logistic regression worked well for product descriptions. So the same thing that worked for product names. The reason is probably because product descriptions are a bit more complex, but not much more complex. So I don't know if you've seen product descriptions, but in many cases, they have just very basic syntax. There's not many complex semantic relationships that are going on, so this is why this approach worked best for both, probably. So in the end, we didn't even train a separate model for this, because so we just took the model that we had trained for product names and applied it to product descriptions. This wasn't the way we had it at first. First, we built a separate model for descriptions, and then we had run that in production, but this wasn't necessary, so it didn't perform better in the end. So now we just use the same model to predict something for product names and product descriptions. Okay, we're almost done. Bear with me. If you remember this nice graph I had, so these are the three models that we have to predict the categories that we have. Now we want to map this to the specific store categories. And to do this, so first of all, what I haven't said yet, how do you merge these different classifications from these different models to one set of predictions? In our case, we just average class probabilities, which is just a very basic approach. So we take the classifications from all of these. So with all of this, we end up with a probability score for each category. And then we just average these probability scores across the different models. You can do something more fancy here and build a separate machine learning model called an ensemble model on top of this, which takes the class probabilities for your categories. And then you add a separate machine learning model which predicts from class probabilities to a unified class probabilities, which where you can, again, test out different methods and see which machine learning model performs best. But for our purposes, we just average them for now. So this is what we have in the current version. After that, we have these predictions for general categories, and now we want to match this to the store-specific ones. And for this, we used word-to-vec similarity. So to do this, we used a word-to-vec model, which was trained on a data set from Google News. Let's not show you this right just now. So the idea is that you want to have a machine learning model which can quantify how similar two strings are. And as I told you before, word-to-vec is a method that is particularly good at this. So what we want to have is if our model predicts, for example, T-shirts, then we want to know that in store A, this corresponds to the category T-shirts and sweatshirts, and in store B, this corresponds to the category shirts in general. And word2vec is very good at estimating these similarities between strings. And what we did there is we used a data set which is commonly used to train word2vec models, a news data set from Google News, and we trained that in the library GenSim. And this is how we got a machine learning model, a word2vec model that can quantify these string similarities, which we can then use to match strings from these general categories to store-specific ones. So first of all, we compute similarity scores between all of these model categories and then all of these store categories that we have. And these similarity scores are in the end just a value between 0 and 1. So 1 means it's very similar, 0 means it's not similar at all. And after we have this, we multiply all these similarity scores with the average class probabilities that we have there. So, yeah. Yeah, but as you can see, so this is an example of how to use word2vec in GenSim. GenSim with the Python library here. You need to download this Google News data set in this format, and then you can just say in GenSim load word2vec format, and then this trains it. And this step just reduces the load on your memory a bit, and then you can just call word2vec model.wv, then in this case computer, for example, and then you get the word vector out of it. So I think technically this is training, but so the training runs here, but it's not magic. In production we have this word2vec model file that we load, but just to show this, training it is just as easy. And if you want to quantify the similarity between two strings now, in our case, there are some functions where you can do that directly with the word2vec model, but we used cosine similarity for this, which you can import from sklearn, for example. So you just have two word vectors here, and then you compute how similar they are, and then you get a final score of how similar these two things are. After you've done this, you can just sort your final scores from highest to lowest, and then you take these as your category recommendations for the specific stores. Now, of course, all of this leads to low confidence scores because we multiply these similarity scores that we get from word2vec with the average class probabilities. So we do this just to capture of how similar two strings are. I mean, we want to combine this information of how confident we are that this is a certain category, but also how confident we are that this category corresponds to a different category in a store. But this leads to rather low confidence scores. But in the end, we are mainly interested in the relative confidence scores, right? So we want to know which category is more relevant than another category. So this still led to reasonable results in the end for us. Okay, almost done. So we, as I said here, in this step, we compute this word2vec similarity between all the 723 categories and all the categories that occur in a model, which is of course compute intensive, and you don't need to do it on demand because the category data in the store, it doesn't change so often. It's relatively stable. Let's say there's a new category once a month, maybe once a week, depends on the store. So you can pre-compute this, luckily. And for this, we simply store it on Google Data Store. You can use any database for this. But just to give you an idea of what this looks like, so this sample here says that in the store called Sunrise Playground, the model category ankle boots corresponds to the category path women, shoes, ankle boots, and this is the similarity, and this is the ID of the category. So this is just how we pre-compute this. We update this regularly so that we don't need to compute it on demand. Okay, now this is an example of how this looks like after we combine all of this and put it in a REST API. So in a REST API, we have this endpoints recommendations/categories, and this is just an API to play around with it. So here you can post an image with a URL, and then what goes on in the background is downloads this image, does all the image classification, and then it outputs the model categories with their confidence scores. So this is just a toy version that we use to check how the model performs. Now the API that we actually use for our customers has a bit of a different endpoint. So you still have recommendations/categories, but then you have the specific store name that you want predictions for, and then you enter the product ID. So all our products in our databases have a product ID by which we can identify them. And then once we have this information, we download product names if they're available, product descriptions, we download the images, we run them through our model, we average, we do the similarity matching, and then we output these results in JSON format. So in this case, this was a backpack, and this corresponded to the category men, accessories, backpacks, and these are categories in this format, together with a confidence score and together with a reference field that we need for our API. We also built, this API is also used in the graphical user interface that we have. So this is here on the product page for a product called Zip-Up Hoodie Men's. And then you can click on the tab recommendations here, and then our API gets triggered for this particular product. And then you can see some recommendations here for which categories might fit to this. Okay. Who in here has worked with Flask before? Okay. Well, maybe 1/3. So here's just a basic example. So after you've done all your machine learning models and all your processing, you want to wrap it up in an API that can be consumed by your customers. And this is just a basic example of how to do it, a simplified one. You need to initialize the Flask app here, and then you need to define a so-called resource that corresponds to a certain URL endpoint. And then here you can define GET requests for HTTP requests. And here you collect some arguments. This is not all the arguments that we use. They are just some examples. So you need to pass a product ID to get to know where we want the predictions for. And this is an optional parameter which you can use to control how many recommendations you get. And this magical function here, which doesn't exist, but which is just to simplify how this resource looks like, this generates all your recommendations. And then you can output it as JSON, put it behind this endpoint here, and then run it. So this is just a basic example of how to do it in Flask. All right, I've talked a lot. This is the pipeline that we had. Now just some next steps. So this is very much work in progress for us. So we're looking to improve this pipeline over time. These are just some steps that we planned for the future. Add more data from our customers. So over time, since we developed this, we got some more customers from other industries, so we can extend this with more data, because right now it's not a lot of data that we have, obviously, so we can improve our accuracies with this. We want to do more image data augmentation, so we haven't done this for our image classifier a lot, rotating and flipping images just to get some more training data. We want to think about using ensemble models instead of averaging the model probabilities. This would be something that improves our accuracies, but yeah, it's just another step that you need to do. We're also thinking about building one large neural network instead of training these different models. So it's a bit unintuitive to train these separate models. In the end, you want to have one big model which predicts the stuff that you're interested in. But this is, of course, not so easy to do it in production and to build one network with these different branches that contains very different data types. But it's an option, so we're considering it. Of course, we want to add more features like prices and brands. We want to replace our transfer learning pipeline with Keras because it's just easier to manage and less boilerplate code. And final step is we want to cache category recommendations in a database. So right now, if you call the recommendations for categories, you compute it on demand. You run it through your models on demand, which, of course, takes some time, and you can speed this up with just pre-computing this. Whenever a new product gets added to our database, we can pre-compute which categories fit to this product, and then when a customer clicks on the page, it just gets the data from the database, and it doesn't need to run the machine learning models live, which just is very helpful for response times.